Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In 1995, Peter Shor unveiled an algorithm that irrevocably altered the trajectory of computational science. His work, Algorithms for Quantum Computation, Discrete Logarithms and Factoring, offered a theoretical roadmap to solutions for problems seemingly intractable for classical computers, ushering in a new era of quantum computation. At the time, the limitations of existing computational models presented a formidable challenge to cryptographers and mathematicians alike, particularly regarding the factorization of large integers and the discrete logarithm problem. These problems, foundational to modern cryptography, underpin the security of countless digital transactions. The theoretical complexity of these tasks, their computational intractability on classical machines, rendered them nearly invulnerable to brute force attacks. Yet, Shor's algorithm posited a radical solution, one rooted in the peculiar laws of quantum mechanics. The core problem Shor addressed centers on the bedrock of modern cryptographic systems, integer factorization, and the discrete logarithm problem. Integer factorization involves decomposing a given integer into its prime factors. For large numbers, this process becomes exceedingly difficult. Its computational complexity increases exponentially with the size of the integer, meaning the time needed to factorize the number grows at an accelerating rate as the number gets larger. The discrete logarithm problem, on the other hand, involves computing the exponent in a modular arithmetic equation. Given a prime number, p, a base number, g, and a result number, a, the problem is to find the integer, x, such that g to the power of x is congruent to a modulo p. Again, for large numbers, this calculation becomes computationally prohibitive. Integer factorization and the discrete logarithm are widely believed to fall within the realm of NP problems, problems for which a solution can be verified efficiently but may be vastly more difficult to find. The prevailing belief regarding their computational difficulty on classical machines is that they are not in P, implying that no polynomial algorithm exists to solve them. If an efficient algorithm existed, it would have significant implications, potentially undermining the security of widely used cryptographic systems like RSA and Diffie-Hellman. Shor's algorithm directly challenges this paradigm. It asserts that a quantum computer, leveraging the principles of quantum mechanics, could solve both the integer factorization and the discrete logarithm problems with remarkable efficiency. The precise claim of the algorithm is that it can factor an integer in polynomial time, meaning the time it takes to factor the integer increases only polynomially with the number of digits in the input. For the discrete logarithm problem, Shor's algorithm similarly claims a polynomial time solution, suggesting that quantum computers could crack cryptography built on these problems quickly. The implications of these claims were profound. If Shor's algorithm could be successfully implemented on a sufficiently powerful quantum computer, it would render many widely used cryptographic systems obsolete. This realization sent ripples throughout the computer science, cryptography, and national security communities, igniting a surge of research into quantum computation and its potential impact. The promise of efficient factorization spurred a re-evaluation of cryptographic security, emphasizing the need for alternative methods and the urgency of developing quantum-resistant cryptography. Shor's work did not offer a fully functional quantum computer. It provided a theoretical framework, a blueprint. The algorithm's power lies in its ability to exploit the principles of quantum mechanics, specifically superposition and entanglement, to explore solutions far more efficiently than classical algorithms. The claims, therefore, are not based on empirical demonstration on a functioning quantum computer, but on rigorous mathematical analysis and theoretical derivation, grounded in the principles of quantum mechanics. In essence, Shor provided a theoretical demonstration, a mathematical proof of concept. The algorithm's power rests in its use of the quantum Fourier transform, enabling the determination of the period of a periodic function. Period finding, a cornerstone of Shor's approach, facilitates the reduction of both the factoring and discrete logarithm problems into a search for periodic patterns. For factoring, the algorithm cleverly transforms the problem into a search for the period of a function related to modular exponentiation. Once the period is found, the prime factors can be extracted through relatively simple calculations. For the discrete logarithm problem, a similar strategy is employed, with the quantum Fourier transform deployed to determine the period of a function connected to exponentiation within a finite field. The period, once known, reveals the discrete logarithm. The immediate impact of Shor's work was largely theoretical. It spurred a race to build a quantum computer powerful enough to implement the algorithm effectively. Although practical, fault-tolerant quantum computers remain a challenge, Shor's algorithm galvanized the field, accelerating research into quantum hardware and software. It forced a profound rethinking of cryptographic security, necessitating the exploration of new, quantum-resisted cryptographic protocols. This work also spurred the development of other quantum algorithms, contributing to the burgeoning field of quantum computing. The work's influence is undeniable. It inspired countless research papers and conferences focusing on quantum computing. It is part of the curriculum for all quantum computing students. It reshaped the theoretical landscape of computational complexity and has made people rethink the ways they approach cryptography. It continues to influence research into quantum computing, driving innovation in fields far beyond the original scope of the work. The quest to build a quantum computer capable of running Shor's algorithm, a quest born from this specific 1995 work of Shor, continues, driven by its potential to revolutionize both cryptography and computation itself. 1995 Peter Shor algorithms for quantum computation, discrete logarithms, and factoring. Let us now fully explore the heart of Shor's algorithm, its quantum underpinnings, the central mathematical tools and its implications. The algorithm's power lies in its exploitation of quantum mechanics, specifically the principles of superposition and entanglement. Unlike classical computers, which manipulate bits representing either 0 or 1, quantum computers employ qubits. Qubits leverage superposition, existing in a probabilistic combination of 0 and 1 simultaneously. This fundamental difference allows quantum computers to explore a vast number of possibilities concurrently, exponentially surpassing the capabilities of their classical counterparts with their sequential processing. This inherent parallelism is the engine driving Shor's ability to solve problems considered intractable for even the most powerful conventional computers. The quantum Fourier transform, or QFT, stands as the central mathematical tool in Shor's algorithm. The QFT is a quantum analog of the classical Fourier transform and facilitates the efficient identification of patterns within the quantum state of a system. Its mathematical foundation involves the utilization of complex numbers and Fourier series. These series decompose a function into a sum of sinusoidal functions. In the context of Shor's algorithm, the QFT is used to determine the period of a function. The function is determined in modular arithmetic, or modulo arithmetic. Modular arithmetic involves performing arithmetic operations within a finite set of integers, where numbers wrap around upon reaching a certain value. The modulus, the QFT, applied to a quantum state encoding a function, efficiently reveals this period. The application of the QFT to the factoring and discrete logarithm problems is where Shor's algorithm truly shines. In the context of integer factoring, the problem is to find the prime factors of a given integer. Shor's algorithm transforms this into a problem of period finding. It uses a specific function related to modular exponentiation. The modular exponentiation function is raised to the power of x modulo n, where r and n are integers, and x is the variable. The QFT is then applied to the output of this function, revealing the period. This period, through further mathematical manipulations, provides the prime factors of the original integer. The discrete logarithm problem, dealing with logarithms in finite groups, also benefits from period finding. In this context, the function, whose period is sought, is related to exponentiation in the finite group. Once the period is found via the QFT, the discrete logarithm can be computed. The claims of Shor's algorithm have undergone rigorous scrutiny and verification. Theoretical analysis has established the potential of the algorithm, and experimental implementations, though limited by the current state of quantum computing technology, have demonstrated its functionality on small-scale instances of both factoring and discrete logarithm problems. While the creation of a fault-tolerant quantum computer capable of breaking modern cryptographic systems remains a significant engineering challenge, the theoretical viability of Shor's algorithm is firmly established. There exist no known mathematical proofs disproving the algorithm's core assertions. Provided a sufficiently large, viable quantum computer is accessible, the impact of Shor's algorithm extends far beyond the realm of pure mathematics and computer science. It has instigated a dramatic shift in the field. The algorithm's potential to compromise widely used cryptographic systems, such as RSA, has prompted a global response to the post-quantum cryptography research. This effort seeks to develop cryptographic algorithms that are resistant to both classical and quantum attacks. Shor's work directly fostered this area of research. Furthermore, the algorithm's influence has spurred the development of quantum algorithms. These new algorithms address a plethora of problems across various domains, from optimization to materials science. It provided a proof of concept, demonstrating the power of quantum computation. The algorithm highlighted the need for innovation in these new fields. The algorithm's influence is also visible in the ongoing pursuit of fault-tolerant quantum computers. The architecture of these machines holds the potential to run Shor's algorithm and other complex quantum algorithms reliably. The construction of such a quantum computer would represent a monumental achievement in both theoretical and experimental physics. In summation, Peter Shor's 1995 work, Algorithms for Quantum Computation, Discrete Logarithms and Factoring, represents a pivotal moment in the history of computation and cryptography. The algorithm's elegant use of quantum superposition, entanglement, and the quantum Fourier transform has ignited a revolution in computer science, fundamentally altering our understanding of computational complexity and security. The challenge of the post-quantum cryptography effort is a direct outcome of this work. This specific work's influence is undeniable. Its foundational role in the development of quantum algorithms and the ongoing search for fault-tolerant quantum computers ensures its legacy will endure. This work continues to shape the future of both computation and information security.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.